We are going to thoroughly discuss the ARMA model, which is another important lecture related to our ongoing time series model discussions. As we always do, we'll be using the Finance Research Gate website as our primary resource for this session. But first, we should quickly review some of the mathematical models that underpin the two distinct components, which together will constitute the complete ARMA model. Indeed, the ARMA model is fundamentally composed of two main parts. We'll begin by examining the first one. This is the autoregressive component, a crucial element that reveals how the previous observations or historical data points of our time series, denoted as xt, directly impact and shape the upcoming or subsequent values, essentially predicting the next period's outcome. So what we're looking at here is what's known as the autoregressive or AR model. We've actually covered this particular model in a dedicated separate video previously, and this specific model, the AR model, it takes on an order which we denote as P. Now this variable P in this context represents the number of past observations or lags of our time series variable xt that you would intuitively consider necessary to include in order to adequately explain and predict the value of x in a subsequent period. The second component of this analysis incorporates the concept of a moving average, and this particular aspect is directly connected to the idea of innovation or shocks. Innovation by its very nature represents something entirely new, something that you simply couldn't have foreseen or predicted based on any prior or historical information available. Therefore, regardless of the specific model or framework you might be employing, any outcome or phenomenon that remains inexplicable that you cannot account for within its parameters is precisely what we categorize as an error or an innovation or indeed a shock. This particular aspect is intrinsically linked to the moving average MA model, which is characterized by its order represented as Q. The variable Q in this context precisely defines the quantity of lagged past errors, or what we term innovations, that are being incorporated into the model's formulation. The ARMA model will combine both the autoregressive component, which depends on past values of X, and any previous innovations or error terms into a single framework. C in this specific instance is merely the constant valuer term. So first we have a mechanism of gradual adjustment, meaning that current conditions are slowly modified and influenced by their previous historical values. And then secondly, we also encounter the phenomenon of short-lived propagation of shocks, which means that any sudden disturbances or impacts tend to dissipate quite quickly. As a practical illustration, consider the fluctuating level of sales that a particular company might experience over a given period. The overall demand for a product often appears to grow quite gradually over an extended period. This is largely due to the fact that customers typically develop a strong sense of loyalty to specific products they use. So it would be highly unusual, for instance, to observe a period of significantly high sales, immediately followed by a subsequent period with very low sales figures. It's highly probable that we'll see some autocorrelation in our sales data because customers frequently remain loyal to a specific product or the company that makes it. This loyalty then leads to sales being autocorrelated throughout time. At the same time, we might encounter events like the launch of some new brand or an advertisement effort that could introduce a fresh innovation in the field of sales, regardless of whether it's a positive or a negative innovation. Within the realm of finance, it is also possible for us to employ the ARMA statistical model as a valuable tool for the purpose of rigorously testing the notion of market efficiency. For example, if we could take into consideration the monthly stock return figures, and then we would proceed to thoroughly analyze and investigate whether the historical autoregressive terms, or indeed the moving average component, are capable of providing a clear explanation for the upcoming, or rather, the future value of that specific monthly stock return. If this is the case, it means that the market is not efficient and a weak form of the efficient market hypothesis. This status implies that by carefully analyzing the historical performance, specifically the past return or any other relevant trading-related information, which is essentially the past return, we can then predict the next monthly rate of return. And that is a clear violation of the weak form of market efficiency. So for the AR model, the property of stationarity is incredibly important. The fundamental reason for this is that we absolutely cannot allow any past shocks or disturbances to accumulate and take over the system. This is because eventually these past influences must inevitably shrink and converge towards zero once we progressively increase the number of lag terms, which is typically represented by the variable k. Therefore, it is crucial that the coefficient associated with the variable p in this equation is strictly less than 1. This condition ensures that the influence of past disturbances or shocks will progressively diminish over time, ultimately leading to a stable system where the variance of the time series xt remains bounded and finite. For example, if the coefficient associated with previous error shocks is found to be greater than 1, this indicates that the impact of those past disturbances is not diminishing, but rather growing, causing the variance to explode or the entire series to drift uncontrollably. Consequently, we can conclude that the underlying process is inherently non-stationary. When we're discussing the MA component, the concept of invertibility is absolutely crucial. What invertibility truly implies is that if we are provided with the observed data, specifically xt, we possess the ability to uniquely determine the exact nature of the underlying shocks, which are represented as ET. So in this particular scenario, we can effectively derive the error term ET by utilizing the current observation xt and incorporating its preceding historical values. It's absolutely critical that the coefficient directly associated with these past values, much like the stability condition for the error term itself, must be strictly less than 1. Therefore, to maintain model stability and ensure proper behavior, the parameter theta must unequivocally be constrained to a value strictly below 1. So in this specific scenario, we observe that the coefficients have significantly shrunk. This implies that our representation remains stable, and crucially, the underlying shocks can be uniquely identified. However, a significant problem emerges. If the parameter theta happens to be greater than 1, then the backward representation quickly becomes unstable and gets entirely out of control. Consequently, this means that multiple distinct shock sequences are able to generate the exact same observed xt series. So, in order to ensure that we observe a truly unique shock consequence, it is essential that the autoregressive parameter, when structured in this particular fashion, must also be strictly less than 1. More often than not, this is precisely what we observe because the influence of past values simply cannot be as substantial or identical to that of the current value. Consequently, as we look further back into the past, the overall effects typically diminish in magnitude. Should this fundamental principle not hold true, then we could potentially face significant problems. Because the innovation in this particular case, if its value, often denoted as theta, is greater than 1, then the innovations themselves cannot be uniquely defined. So, once we've selected the specific data series, we then proceed to analyze its autocorrelation. The autocorrelation coefficient itself, and also the partial autocorrelation coefficient fig. If both of these indicators show a decay, it suggests that we are observing both types of effects, the autocorrelation effect and the partial autocorrelation effect. It's crucial to remember that autocorrelation allows, for example, xt minus 2 to relate and correlate with xt. This happens through an indirect effect, specifically via xt minus 1, which acts as the intermediate lag. The PACF, on the other hand, is designed to isolate and measure only the direct impact between observations. It specifically filters out any indirect effects that might be present. So, if we observe that the ACF shows a significant correlation, but the PACF does not show a significant correlation for any particular lag, this indicates that the observed correlation in the ACF is likely due to indirect effects. And let's say, in this case, the PACF for x is not significant. T minus 2 is not particularly significant, but the autocorrelation function, or ACF, definitely is. This clearly indicates that the xt minus 1 value is the primary influencing factor here. This is the fundamental reason why the variable xt minus 2 exhibits a clear correlation with xt, and simultaneously we must acknowledge that there is a direct influence, of course, emanating from xt minus 1 upon xt. So, when we observe a significant autocorrelation function, or ACF, but simultaneously a non-significant partial autocorrelation function, or PACF, this pattern clearly indicates that there isn't a direct immediate correlation existing between a specific past observation, often referred to as the lag or the autoregressive term, and the present current value of our variable x. However, if the partial autocorrelation function, or PACF, shows a clear decay over time, this indicates the presence of what we call error shocks. This is because simply controlling for an intermediate lag in the model will not be sufficient to completely remove the persistent effect of these underlying errors or innovations. For instance, if we were to control for the variable xt minus 1, and then if xt minus 2 is found to be statistically significant, it suggests that we might have an error term here, which is actually stemming from xt minus 2. This particular error term is, by its very definition, not correlated with xt minus 1. So, if the partial autocorrelation function does not sharply drop to 0, it strongly indicates that we might be encountering some significant issues or errors related to the proper specification of our autoregressive terms within the model. Alright, let's put this into action right now by looking at an example. Our first step is to visit the website, and then we need to carefully select the appropriate time series. And then I'll go ahead and select a recent data sample, specifically from the years 2000 through 2024, and then apply that.
Let's move forward and select the stock's monthly return data.
I will leave these selection boxes completely empty so that I can ensure all available firms are chosen, and then I will proceed to submit my application. And by performing that action, we successfully generated Series A, which now holds the complete monthly stock return figures for the overall market. Now, if we proceed to scroll further down on this page, we have the descriptive statistics. Now, the very first and most important thing we should do before we even begin the process of constructing our model is to carefully examine the data by looking at a chart of its progression over time. This initial visual inspection is crucial just to determine if there might be any indication of some sort of autocorrelation present within the dataset. And we can identify if there's any kind of autocorrelation present in our data, so let's proceed with an actual statistical test to confirm this. The initial step involves examining the autocorrelation diagnostic plot, which provides visual evidence of these patterns. While we have the option to increase the number of lags considered, I believe that for data collected on a monthly basis, a lag of 12 periods will be perfectly sufficient for our purposes. Alright, let's proceed now and open up this particular box. And as we can clearly observe right here, the autocorrelation coefficient value is indeed quite significant, almost reaching full statistical significance when we consider it at just one lag. The value is 0.07, so the autocorrelation, in terms of its magnitude, isn't particularly large. From a statistical standpoint, it's only barely significant, meaning its actual impact could potentially be somewhere between 4 and 5%. It falls just outside of this expected range. Any value falling within this range indicates that autocorrelation is not significant. When we examine the partial autocorrelation, it clearly shows that there is a significant effect originating directly from the very first lag. This particular finding is quite logical and makes perfect sense. Because we don't have any intermediate lags that are significant, it naturally follows that by default, the autocorrelation function will be significant for the first lag. Consequently, this also implies that the partial autocorrelation will likewise be significant at that same initial lag. Considering the characteristics of our data, it's quite possible that a simple AR1 model could prove to be entirely adequate for our immediate purposes. However, to ensure a more robust and comprehensive analysis, let's go ahead and implement an ARMA model. This approach will then explicitly allow the inherent innovation and unexpected shocks to fully influence the dynamics of our observed time series. The diagnostic analysis conducted here strongly suggests that the moving average component may not actually have any substantial role to play, primarily because the partial autocorrelation function, specifically after the very first lag, is simply not demonstrating a statistically significant impact. This is particularly relevant if we encounter a scenario where, for instance, the autocorrelation function abruptly terminates, specifically after observing just the initial lag. However, if the partial autocorrelation function, or PSCF, clearly indicates a significant correlation at either the second or the third lag, this strongly suggests that a moving average component, or MA, is absolutely essential and must be incorporated into our model. The fundamental reason behind this necessity is that the error terms, specifically those observed at these particular lags, will effectively account for and explain the substantial direct influence originating from the past values of xt, namely xt2 and xt3, upon the current value of x. So, what this implies is that the PSCF's function will be to exclusively account for the indirect influence that arises from the various intermediate time delays or lags in the process. However, the inherent errors within this system cannot be effectively controlled. Therefore, if we observe a significant effect that is not clearly suggested by the autocorrelation function, ACF, nor by the partial autocorrelation function, PSCF, then this strongly indicates that new innovations are indeed playing a crucial role in the process. Consequently, we must also incorporate the moving average MA component. However, for the purposes of illustrating this concept, we will employ an ARMA model, specifically one component for the autoregressive aspect and another for the moving average aspect. We are now turning our attention to the classical ARMA discussion. Here we have one example, here's another one, and then we'll just save the residuals from the ARMA model. And then, after that, we'll proceed to fit the model to our available dataset. The residual, quite simply, represents the error or the difference. Will be the residual error term from the ARMA model. So, in this particular example, we concluded our analysis at this stage incorporating only a single distinct term. The error term in this specific scenario is what we are actively working to estimate, which we refer to as the residuals. These residuals fundamentally represent the difference between the actual observed value and the value that we have predicted or estimated. I'm going to use the hat right here. And XD, it is derived from the conceptual framework of Model C. One particular autoregressive component, or the stock's financial return over a single month. Yeah, negative. And one leg of innovation. The fundamental distinction, in essence, is solely attributable to this particular error term. And the significant reason why we are meticulously preserving these calculated residuals is to enable us to comprehensively investigate and understand both the autocorrelation and the partial autocorrelation pattern. For our model to be considered truly good and successful, its output or residuals must then conform to the characteristics of white noise. What this essentially means is that we should not detect any statistically significant autocorrelation, nor any partial autocorrelation within the series. This fundamental property defines what we understand as white noise. If our predictive model is indeed good, then we can confidently proceed to fit it. Now, at this point, we have derived a constant that will precisely inform you about the average monthly return experienced by the market. So, here we have the autoregressive component, which is often called the AR part. The coefficient here is negative, meaning that if there is an overshoot in one particular period, then a correction will occur in the subsequent period. This precisely explains the reason why we observe a negative sign. Does this hold any real significance? It's currently at 10%. So, when we look at a 5% significance level, we can clearly see that it is not statistically significant. So this coefficient that we're focusing on is simply represented by this specific component, this one right here. So the final result that we've obtained is negative 0.515. Next, we'll examine the moving average coefficient. This particular coefficient indicates that any past innovation will directly influence the subsequent monthly return of the market. Our findings reveal that the p-value associated with this is statistically significant at the 5% level. Therefore, we can confidently assert that a distinct moving average or MA effect is clearly evident. And somehow we've observed some kind of an autoregressive effect within the data, but it's only found to be statistically significant at the 10% alpha level. Therefore, the specific coefficient we're examining here directly reflects the parameter theta, which is precisely 0.59.
This is number 5.
Now, next, we're going to take a look at the residuals that come from the model. That appears to be white noise. However, we must conduct a formal test to confirm that. Therefore, if you could please scroll down to the end of the page, you will find our autocorrelation diagnostic box. Looking at this, it might appear different visually, but the core concept we're discussing is fundamentally the same. Here, we've established a clear boundary, which includes both an upper threshold and a corresponding lower threshold. So, if our calculated correlation coefficient either goes beyond this upper limit or drops below the designated lower line, this would then signify that we are indeed observing a statistically significant level of autocorrelation.
So, for the original series, you'll want to select only the residuals part.
And then we'll need to determine if we have a white noise process after applying the ARMA model.
Observing this, we can clearly see that the specific value lies comfortably within the established acceptable range. This outcome strongly indicates that we do not possess any statistically significant serial autocorrelation within the error terms of our current analysis. This, in turn, provides compelling evidence that our predictive model has indeed effectively and successfully captured any potential lagged autocorrelation that might have been present. Because in this case, the error term does not exhibit any significant autocorrelation at lags 1, 2, 3, and 4, and this holds true all the way up to lag 40. Even then, there is still no significant autocorrelation present. The same observation applies equally to the partial autocorrelation function. We don't have any new information or innovation within the residual term itself, which means it cannot explain the subsequent period's residual. This implies that our residuals are effectively white noise, achieved through the process of estimating or fitting the ARMA model in this particular scenario.
That concludes our session for today. Thank you all for listening.